So hello there, and welcome to another tutorial. My name is Tanmay Bakshi, and today we're going to be going over how you can use Keras totally within a Swift environment in order to create two CoreML models that can help you interpolate between two digits that users write on an iPad application. Now, in essence, the point of this app is to interpolate between two MNIST digits. Now, the way it works is by using autoencoders. If you don't know what an autoencoder is, go ahead and watch my video on the topic at the link in the description. Now, in essence, autoencoders allow you to, encode and then decode information to have the same output as there was input in a neural network. The interesting part about autoencoders is that it forces the neural network to create a compressed representation of the input you give it in order to decompress that into the output because of the neural network architecture. Now though, let's take a look at how you can actually go from step 1, training your neural network, to the final step, deploying it on an iOS application directly through Keras and entirely within a Swift environment. Now, you're probably wondering, well, Keras is a Python library. Why would you actually go ahead and run it on Swift? And well, there's actually a very interesting new library available for Swift called PythonKit. It's available with the new Swift 5, and the interesting part is that it lets you bridge between Python to Swift directly and natively within your Swift code. And so we're going to be training a Keras model directly through Swift using PythonKit. You can find out more about this Swift bridging of Python at my first episode of Swift Today, again in the link in the description. But now let's take a look at how exactly we'll be doing the interpolation. Now let's start off by discussing neural network architecture. Now, let's take a look at how the encoder works. Of course, the encoder is a very simple neural network that takes in an image. The image is going to be 28 by 28 with a little bit of an exception. Now, you see, CoreML is a great library. But CoreML isn't necessarily very versatile when it comes to working with Swift, and it isn't very versatile when it comes to working with images. The reason is because it was originally developed for Apple by Apple in Objective-C and has not been completely ported to Swift. Therefore, working with it is not very pleasant, because you need to transition between doubles and NS numbers and tons of different types of variables. However, there is a great library on GitHub called CoreML helpers. It makes life a lot easier when you're working with CoreML, specifically with images. There will be a link to that in the description below as well. Now, because of how CoreML helpers works, and because of how CoreML works, there needs to be a third channel at the end of this image. Now, usually, you would only have one channel at the end of the image because, well, you've only got grayscale values. You've only got scale values on the scale of 0 to 1 in one channel because MNIST is, again, grayscale. It's not red, green, blue requiring 3 channels of grayscale. However, because we are working with CoreML, as I mentioned, we're going to be duplicating that grayscale channel 3 times to create a pseudo RGB image that'll look the exact same, act the exact same, just has a few extra parameters in the neural network to deal with 2 extra channels. And so there's not really that much happening here, except for the fact that we're going to do a few NumPy tricks to turn this array from 28 by 28 by 1 to 28 by 28 by 3, because Keras comes with a 28, 28, 1 formatting. That's really, really simple. I'll show you how to do it within Swift again. But from there, there's going to be a simple convolutional neural network, right, a CNN, that goes ahead and takes this image and outputs a very simple vector. Now this vector will be, say, 300, right? It's going to be a tuple of 300 length. This is what the input or the output shape would be of the final convolutional neural network when it has a dense layer and, of course, a flattened layer before that attached. Now this vector over here, this 300 vector, perfectly represents the input that you gave the model. Now, one thing you should note, though, is that 28 by 28, right? How much is that? What's 28 by 28? That's 784, okay? So we're dealing with 784 values here. Now, this 784 is being compressed into 300 that contains essentially the same information. However, that information needs to be decoded by another neural network. And this is the interesting part. Essentially, this will undergo the reverse to get back to a 28 by 28 by 3 image. Essentially, this 300 size vector will be fed back into another convolutional neural network, which will go ahead and convert that into 28 by 28 by 3 image. Now, at the end, we should have almost exactly what we put into the neural network in the beginning to get this vector. Now, the interesting part, though, is that let's just say you take two different digits. Say we have these two boxes over here, and if I were to draw a 5 in one of them, and I have another box over here where I draw a 7. Now, when these go through the encoders, right, what happens is you get an encoding for each one. You get a 300 size vector for each number, okay? Now, once you've got those 300 length vectors, you can go ahead and interpolate between those vectors, okay? Now, let's just call this one A and this one B, okay? You've got these two different vectors. Now, let's just say you want to go from A to B. Every point within A of the vector space and B in the vector space, you want to interpolate between. There's a custom function that I've put together for that, again, in Swift. And what you can actually do is tell it how many steps in between you want from A to B. Now, let's just say we want, say, 1,000 frames in between A and B. We go ahead and generate those 1,000 vectors that are individual stepping stones that go slowly from A to B. And then in total, we've got 1,002 total frames, including A and B. Now, the 1,002 frames can individually be decoded with the neural network that we built in order to generate 1,002 proper images of what looks exactly in between A and B, just a little bit off from A, just a little bit towards B. We can generate all of that and create a very, very smooth animation that runs at 60 frames per second for a length of around 17 seconds, and it gives us a really nice interpolation between those two digits. Again, this is all happening directly on device. There's no cloud involved here. And those 1,000 inference operations are happening in under a second using CoreML batch predictions on the iPad Pro's neural engine. All right, so now let's get ahead to a demo of how the application works. And after that demo, we'll take a look at how you can actually implement this application. All right, now let's take a look at a demo of the application in action. This is the user interface. Now, over here we've got a black patch. Now, on this patch, you can actually go ahead and draw. As you move your finger, it draws, and these are the same proportions as the 28 by 28 image that we're going to be scaling down to. Now, of course, because the iPad Pro is such a high-resolution display, this is highly scaled up from 28 to 28. 28 by 28. So when you go ahead and use any of the functions, it'll go ahead and scale it down to 28 by 28, and then when it gets output from the neural network, it'll scale it up, therefore making it blurrier. So if I go ahead and clear this, I can go ahead and actually draw on the display itself. So if I go ahead and draw a digit, say 5, right? Now, if I want to see what the neural network thinks this 5 looks like, I just click the first button called Encode Decode. It'll run it through the autoencoder and do nothing else. So I do that, and this is what that 5 looks like to the neural network. Essentially, the exact same thing that I draw, except a little lower resolution, but it still retains the shape, the general idea, and how exactly I was trying to create that 5. So I'm going to go ahead and clear, and let's draw the number, say, 6. Right, so I draw 6. Now, let's just save this 6 as number 1, okay? So save encoding number 1 is what I'm going to click. Now, let's go ahead and draw another number, say a 4, okay? Now, a 4 and a 6 look very, very different. In fact, if I were to go ahead and decode this 4, this is what the neural network thinks this looks like. I'm going to go ahead and draw one more, all right? And I'm going to save it as number 2. Okay, now what I'm going to do is I'm going to tell the iPad to actually go between those two numbers, calculate 1,000 frames in between, and run that animation at 60 frames a second, and watch how fast it shows me the first digit. It'll take just around a second. And just like that, it starts the animation. Now, as you can see, it starts off as a 6, but slowly but surely, in under 17 seconds, it goes ahead and slowly interpolates from that 6 to the number 4 that I wrote, in the same style as I wrote it, and just like how I would have expected it to turn out. It's still animating, but right as it's done, we should see the final 4. Now, this is what I'm going to be showing you how to build with the help of CoreML, Keras, an autoencoder with the architecture I described just a moment ago, and of course running in real time directly on your iPad Pro. So now, let's go ahead and take a look at how you can go ahead and build this application. Alright, so welcome back to the code part, and now let's take a look at how exactly you can implement this entire autoencoder system. Let's start out with the actual neural network model itself, the main part. Now, we're going to be using 2 different Swift toolchains. As you can see right now, I've got the latest Swift 5 toolchain installed. However, for the iOS application, you're going to need to use the default Xcode 10.1 or whatever Xcode you're working with toolchain. Reason is because these snapshots don't come with the iOS development frameworks pre-installed, and therefore you will not be able to build iOS applications with these toolchains. But let's get into the code. Now, this over here is the actual command line application currently loading up. Here we are. That's going to enable us to train the model and then convert it to a CoreML model. Now, let's go through this code and take a look at how it works. First of all, you'll notice that we have 2 main functions, the train function and the convert model to CoreML function. Now, the train function is meant to use Keras to train a model, and then from there save 3 different models: the full autoencoder, just the encoder, and then just the decoder. The next function is meant to take those 3 models and take just 2 of them, the encoder and the decoder, and then save them as CoreML models or ML models. Now, over here I've got a little bit of code in the script that basically will go through the command line arguments that were passed to the Swift program. And if the argument is train, then it'll go ahead and train. If it's CoreML, then it'll go ahead and convert to CoreML. Now let's take a look at the train function. Now, in the train function, the first thing we're doing is we're doing a few basic imports. So, just to give you an idea, this is what the equivalent would be in Python. So, let Keras is equal to python.import Keras. In Python, of course, this would just be import Keras. The next layer, or the next line, would be from Keras, or import Keras layers as layers. The next one would be something like from Keras.datasets import mnist, and then the next one would be from Keras.models import sequential, and I made a typo here, but we can fix that. Sequential, and then this one, of course, would be very simple: import numpy as np. So we're able to translate that Python code directly to Swift. Again, if you have not seen my Swift Today episode where I cover this kind of bridging, you need to take a look at that before you get back here. But anyway, back to the point. Let's go ahead and actually import the mnist data itself. Now, this in Python would quite literally just be this much code. Mnist data is equal to mnist.load data. Apart from that, everything is the exact same. Like, the only thing you're really adding here is the let to tell Swift that you're creating a constant. Next, you're creating xtrain and xtest. Again, this would be the exact same code in Python. It's that nice translating from Python to Swift. The only thing you're adding is var to tell Swift that this is a variable. I can go ahead and remove those comments since I don't need them, but that gives you an idea as to how convenient that bridging truly is. Now, just to tell you here, over here I'm loading the X train. I'm dividing all those images that are provided in the X train by 255 in order to reduce from a uint 8, which is, the standard RGB 255 range, over to 0 to 1 range. And I'm doing the same thing for the testing data. And then over here, I change the shape, as I mentioned, from 2828.1 to 28.3. That's what we're doing with these two lines of code. Now then I just go ahead and print out those two lines of, with these two lines of code, the shapes of the xtrain and xtest arrays, and then we go ahead and do the interesting part. I declare two different models, my encoder model and my decoder model. The encoder model is essentially going to take these layers over here, and it's going to encode the input, which is of size 2823, or shape 2023, and it's going to encode it into a length of 300 in terms of a vector. Now, something you should notice here is that there's a little bit of, sour syntax here. The syntactic sugar provided by PythonKit is great in most circumstances, but it kind of breaks down here because we're doing a relatively complex query. You see, what I'm trying to do is I'm trying to take this layer that I define here, right? And I'm trying to do encoder.add, call that function, and pass it here. Now, this is something that for some reason crashes not just PythonKit, but the whole Xcode environment. So if I remove that code, and instead I were to dynamically get the add function and then call it manually with the dynamically call function, it goes ahead and works. So to give you an idea, for this line of code, the equivalent Python would be encoder.add, and then this whole, I guess you could say layer, this layer definition, and then you would just be changing these colons to equal signs, and then you would have you would have completely normal Python code. However, this is just most probably a temporary inconvenience as they're still working on Swift 5 and PythonKit. And I do expect that within the months to come, they will be fixing these issues. But next, though, I also declare my decoder model. Of course, the decoder model is essentially the encoder flipped around. It'll first of all go ahead and take this 300 vector, convert it to 392, reshape it to 7 by 7 by 8, and then run the whole neural network backwards, essentially. And at the end, instead of having 16 channels in the final layer, I have 3 channels for red, green, and blue with a sigmoid activation in order to bring each value from a scale of 0 to 1. Then this autoencoder model essentially just puts the encoder and decoder into one model. This isn't necessary, but I just save it for convenience if I want to test it out with Keras. Then I go ahead and also for convenience of training. Then I go ahead and compile. Now I use the atom in terms of the optimizer, and then the binary cross entropy loss. Now I don't use, of course, the accuracy metric because that wouldn't give me much useful information. Next, I go ahead and get a summary of the model just to get an idea of what it looks like, and then I go ahead and fit it on xtrain. The reason I'm not using ytrain is because, of course, there are no labels. I'm trying to predict xtrain based off of xtrain as input. Same thing for validation data, x for test, in and out. I run this from just 3 epochs. Then again, you've got to realize that we're running this whole network on a MacBook Pro. This is not being sent to any cloud. And it actually works very well, better than you might expect. However, again, you do have to realize that it's still a MacBook Pro, and for that reason, if I want to spend only around 10 minutes training, or even less than that, I'm only going to do 3 epochs. You could, of course, do more. It would just take more time. However, from there, I just go ahead and save those models. Again, this would be the exact same Python code for these 3 lines in specific. Now, the next function, the convert model to CoreML function, is where we do a little bit more of the interesting stuff. So I first of all go ahead and import the CoreML tools. And just by the way, pretty ironically, Apple themselves created a toolkit for their own software that only runs in Python and not in Swift. And then they had to build a bridge from Python to Swift to get their own software to run on their own language. It's a pretty interesting situation, but it's one that arises because, of course, so many people use Python, but now as Swift developers, you can leverage all of this within Swift as well. So let's go ahead and take a look at the encoder. Essentially, I'm calling CoreML tools, I'm calling its Keras converter, and converting specifically this model at this path. Now, these three parameters are going to do one thing. They're going to make it so that instead of taking an ML multi-array, which is painful to work with, instead, CoreML is going to take a CD pixel buffer, which CoreML helpers will help us convert to. From there, the decoder, of course, this is going to output an ML multi-array of shape 28 by 28 by 3. But again, thankfully, CoreML helpers will help us convert from that ML multi-array to an image that we can show on a UI image view. From there, the encoder and decoder models will be saved, and then, of course, that same little script that I was talking about. Now, if I go ahead and build this with Command B, it says build succeeded, and now we can go ahead and actually use this code. So if I go ahead and show the resulting binary in Finder, as you can see, this is where it's located. Now I can go to iter, which is my preferred terminal environment, make this a little bit bigger, and then let's go ahead and change directories into where this binary is located. Now this is where the binary is located, and it's called Autoencoder Interpolate. So if I go ahead and run that binary, I can go ahead and give it a command, like for example, the train command. Now this is almost all happening within Python, and as you can see, it goes ahead and gives me an exception. Let's go ahead and take a look at why it's giving me this exception. Okay, so apparently the reason is because my TensorFlow version is too new, or yes, it's using Python 3.7. So in order to fix this, I'm going to go ahead and do brew uninstall Python at 3. I'm going to go ahead and speed this clip up so you don't need to see paint dry. Alright, so now we're back. I have uninstalled and unlinked Python 3 because, of course, it's not impossible, but it is relatively difficult to tell PythonKit exactly which Python environment you're looking to run in. But anyway, let's get back to the point. Of course, this is running entirely within Python, but we didn't have to write a single line of Python code. It's all running through our Swift code. As you can see, it goes ahead and prints out this description of the model, which isn't necessarily very descriptive because it's just telling us we've got one encoder and one decoder, but it works. It tells me the number of parameters, only 240,000 parameters. Now, of course, I could let this keep going. It should only take like 2-3 minutes maximum for each epoch, and as you can see, the loss is steadily going down, so we do have a good architecture. However, again, I don't want you to have to watch paint dry, so I've already trained these models. However, I will show you the way I convert to CoreML. So I'm going to go ahead and run Control-C to stop this training, and now let's go back and give it the next command, the CoreML command. So with this CoreML command, it should go ahead and use the pre-trained models to convert to CoreML format. As you can see, the encoder and the decoder are both done. This is where the decoder's model starts and ends, and this is where the encoder starts and ends. All right, now let's do the interesting part. Let's take a look at the iOS app. Now I'm going to go ahead and open up a new Xcode project called Digit Interpolator. Now for this, of course, we won't have a successful build because we're using the wrong Swift toolchain. If I were to switch back to my Xcode 10.1, then go ahead and clean just to be on the safe side and build, as you can see, we should get a successful build any moment now, and almost there. 47 to 50 tasks. There we go, build succeeded. Now, in the view controller.swift file, we've got a lot of code, but we'll get into it in just a moment. First of all, let's take a look at the ML models. First of all, I've got my encoder interpolate ML model. Now, of course, this is only 484 kilobytes, which is basically nothing. It takes in an image and returns a multi-array of 300. This is the encoded vector. Same thing for the decoder. Now, if I go ahead to my main.storyboard, in the main storyboard, you can see that I've got a very simple user interface. In the middle, I've actually got two elements. over here. Of course, it looks like one, but it's actually two. I've got one UI image view, and I've got one UI view, okay? This UI view is black, and it's actually a custom class called drawView, and this UI image view currently has no image. Now, of course, if I were to just drag this UI image view onto the UI view, it would become part of the UI view. However, if I were to just, inside of the metrics part of Xcode, change its X and Y to the same, or to that of the UI view, it just stacks both of them on top of each other. Now, by default, this image view is hidden. As you can see, I have ticked the hidden element over here. And so you will not be able to see this, you will not be able to interact with it, you will only be able to interact with the UI view underneath. However, let's get to the buttons for just a moment. Now, I've got 5 main buttons: the encode decode button, which will just run it through the autoencoder; save encoding number 1, which will save this as, well, the first digit; save encoding number 2, which does, well, the same in the other direction; and the interpolate button, and of course a clear button to clear your draw view. Now, if we go to the viewcontroller.swift file and make this code a little bigger, as you can see, first of all, I've got an extension to ML multi-array, which will essentially take the current multi-array and convert it to a double array upon request. This is a computed property as part of the extension, and of course you can access this to get a double array. Now, from there, I've also got an extension to array, but only if the element within the array is a double. If you've got an array of this type over here, double, then this extension will be valid, and you'll be able to convert whatever array you've got to an ML multi-array, and you'll also be able to pass it a shape in order to create that multi-array, and then provide it values, and then return it to you. Now, from line 40 onwards to around line 87, including struct line and class drawView, this is code inspired by YouTubers named MacHeads101. There will be a link to his video also in the description below. Essentially, it's a very, very simple view that enables you to draw based off of the points on which you do, the points where you're touching on screen. It's actually very, very simple class, but I've gone ahead and added my own custom function here. Now, this function essentially allows me to convert this UI view into a UI image that CoreML helpers can convert into a CV pixel buffer to feed into the actual CoreML models. We'll talk about where this fits in just a moment. Next, though, let's take a look at the actual view controller class. Of course, it inherits from UI view controller and doesn't need to conform to any other protocols, but it has simply 2 IB outlets: the draw view, where you're going to draw, and the interpolate view, which is where we're going to be showing all those frames in the animation. It's a UI image view. Then I declared 2 different models, the encoder and decoder models, as well as 2 optional arrays, double arrays, encoding 1 and encoding 2. By default, they're nil. No value is given to them. Then I declare 3 variables over here: interpolated images, which are all the different UI image frames; interpolation index, which is the integer that actually covers the index of interpolation, which is which frame you're currently on in this array. And then, of course, there's the animation timer, which runs once every 60th of a second to show you the next frame in the array by incrementing the index. Now, there's nothing we need to do in view.did_load. Everything is done by the user. Over here, I've got a simple function that goes ahead and takes 2 vectors and interpolates between them. Now, this clear function is where the interesting stuff starts happening. So in the clear function, essentially what I do is, if the UI image view, the interpolate view, is currently up, then I hide that and I show the draw view. Then I tell the draw view that there are no lines that the user has created, and I tell it set needs display, which is a class in UI view, or it's a function in the class of UI view that tells draw view to redraw whatever it is that it needs on screen. Of course, over here, if the animation timer is actually not nil, it'll go ahead and invalidate it as well, just to stop it from animating, in case you want to stop the animation in between. Now, there's also another function over here to get the current encoding. Essentially, this will convert the current image on the draw view into, well, a UI image. And then it'll run that image through the encoder. Again, using CoreML helpers, I can convert that to a pixel buffer of width and height 28, and then forcefully unwrap that optional. Again, I highly recommend that you handle errors, but for the sake of simplicity, I'm not doing that. I go ahead and take the output, which is the encoded representation, and then I go ahead and actually set that encoded representation to 255th of that encoded representation. So basically divide that by 255. I then go ahead and return that encoded representation to whatever called this function. Now after that, I've got the IB action for the function that does the encode decode. Essentially, it'll call the function that we just talked about, get current encoding. It'll run that through the decoder. It will go ahead and hide the draw view. It'll go ahead and show the interpolate view, and then it'll set its image to whatever the decoder neural network gave it. And of course, again, using CoreML helpers to reduce whatever it is that I would need to do to one simple line of code. Now, there are two functions over here that do basically the same thing, save encoding 1 and save encoding 2, except save encoding 1 will get the current encoding's double array into encoding 1 and then clear, whereas save encoding 2 will do that into encoding 2 and then clear. Then we've got the really interesting function. This function goes ahead and actually interpolates between two different encodings. First of all, it'll go ahead and make sure that you've actually put both of the encodings. If you haven't, it won't do anything. Then it'll go ahead and take those two vectors and it'll interpolate between them manually. Then it'll go ahead and take those interpolated vectors and provide them as inputs to the decoder model. Now here I'm using the batch prediction API to do it really fast instead of sending predictions one by one. From there, I go ahead and actually convert those to UI images. I actually set each of those images to each of the frames in the interpolated images variable that we were talking about in the actual class. I hide the draw view, show the interpolate view, and then I set the animate timer to run a block of code every 1/60th of a second. I tell it that it should repeat and that it should call this block of code. Essentially, what it's going to do is it's going to show the next frame if there is a frame. If there are no frames, it'll invalidate itself and it'll go ahead and nil that timer. Of course, we don't need to necessarily make it nil, but just for the sake of cleanliness and memory management, I can go ahead and do that. And that is surprisingly all the code there is to the digit interpolator. Of course, I'm not counting all of the code that goes behind CoreML helpers. Thank you to Matish for actually putting that up and making that accessible through GitHub. Sorry if I'm not pronouncing your name correctly, but that was a quick tutorial on how you can use Swift. A complete Swift environment, no Python involved whatsoever, to create a complex machine learning model using only a few lines of code that enables your users to draw digits and interpolate between them. The possibilities here are really almost endless in terms of what you can do. But that was a quick tutorial on how you can do so using Swift and Python. I do hope you enjoyed. If you did, make sure to leave a like down below, and also do make sure to leave a comment if you have any feedback or suggestions or any questions, and I'd love to get back to you. Apart from that, if you really do like my content and you want to see more of it, please do make sure to subscribe to the YouTube channel, as it really does help out a lot. And apart from that, if you would like to see this content right as it comes out, make sure to turn on notifications to be notified, of course, whenever I release new videos. Again, thank you very much for joining in. That's what I had for this tutorial. I do hope you enjoyed. Goodbye.